everyone, and welcome back to Sustainability and Engineering. Today's video, it's not about calculation, it's not about brands, and it's not about one specific HVAC system. Today, we are answering a very practical question. Which HVAC system should I select for a project? Will it be DX? Will it be VRF? Will it be FCU with chill water? Or will it be district cooling system? Every system works, but not every system works everywhere. By the end of this video, you will be able to look at any project, understand how the building will behave, and confidently decide which HVAC system fits best for the project. Let's start with something very important. Most HVAC problems do not come from poor installation. They come from wrong system selections. If you select the wrong system, energy bills increase, comfort complaint starts, maintenance becomes a headache, and client loses trust. If you select the right system, the building runs smoothly for 20 years, maintenance is predictable, and energy consumption stays under control. This is why HVAC system selection is a consultant's responsibility, not a contractor's preference. Before selecting any system, we must stop and ask, what kind of building is this? System selection depends on building type, operating hours, load variation, level of control required, and client budget and lifecycle costs. There is no best HVAC system in the world. There is only a best system for a specific project. A villa, a hospital, and a shopping mall behave very differently. A villa runs mostly evenings and nights. An office runs daytime, and a hospital runs 24/7. If we apply the same HVAC logic everywhere, we guarantee failure somewhere. So before selecting any system, we must understand how the building will be used. Let's start with the most common system, that is DX system. DX means direct expansion. Cooling happens directly inside the indoor unit using refrigerant. Examples are split AC package units. DX systems are simple and easy to install with low initial cost. This is why they are very popular. DX systems are perfect when areas are small, operation hours are limited, and each space is independent. Typical good applications for DX systems are villas, small offices, retail shops, or individual stores. But DX system struggles when the building becomes large, many zones operate at different times, and energy efficiency becomes important. So DX systems are not bad, it just has limitations. Now let's talk about limitations of DX system. And this is very important. Every system has a place where it works well and a place where it should not be forced. The first limitation for DX system is poor efficiency at scale. Let us go into this. DX system works efficiently when the project is small, but as the building size increases, we end up installing many individual outdoor units. Each unit runs independently with no load sharing and no optimization between zones. So instead of one optimized system, we get many small compressors running inefficiently, especially in hot climates in regions like Middle East, UAE. The second limitation for DX system is limited zoning. With DX systems, zoning flexibility is restricted. One outdoor unit usually serves one indoor unit, or at best, a very small group. This makes it difficult to handle different occupancy patterns, different heat loads, and different operating schedules. As a result, some areas become overcooled while others remain uncomfortable. The third limitation for DX is higher maintenance in large projects. In large buildings, DX means many outdoor units, many compressors, many refrigerant circuits, and many potential failure points. Maintenance becomes repetitive, costly, and difficult to manage. A single failure may not shut down the entire building, but frequent failures create long-term operational problems. So the key takeaway here is simple. DX systems are not bad systems. They are just not meant for large or complex buildings. When the project scale increases, we must move towards smarter, more centralized solutions. And that brings us naturally to the next system, that is VRF. Now that we understand the limitations of DX system, let's move to the next level of HVAC solutions, that's VRF systems. VRF stands for Variable Refrigerant Flow. In simple terms, VRF is an intelligent version of DX system. Instead of running the compressor at a fixed capacity, a VRF system continuously adjusts the amount of refrigerant based on the actual cooling demand of the building. So when the demand is low, the system slows down. When the demand increases, the system ramps up. This ability to modulate capacity is what makes VRF much more efficient than conventional DX systems. Another key advantage of VRF is control. With VRF, each indoor unit can be controlled independently. Different zones can operate at different set points. Different spaces can run on different schedules. This makes VRF ideal for buildings where occupancy and usage vary throughout the day. In short, VRF systems offer better energy efficiency, superior zoning flexibility, and improved occupant comfort. However, VRF is not just plug-and-play solution. It requires proper design, correct refrigerant piping, safety checks, and well-defined control strategy. When designed correctly, VRF becomes one of the most effective HVAC systems for medium to large buildings. In the next slide, we will clearly see where VRF system works best, and just as importantly, where they should be avoided. Now that we understand what a VRF system is, the next logical question is, where does VRF actually make sense? VRF system performs best in buildings where flexibility and zoning are important. Let's start with office buildings. In offices, different departments operate at different times, meeting rooms have high peak loads, workstations have lower steady loads. With VRF, each zone can respond independently. A meeting room can cool aggressively, while an adjacent office operates at much lower load. This is exactly where VRF excels. Now let's talk about hotels. Hotels are one of the best applications for VRF. Why would you ask? Because every room is an independent zone, occupancy keeps changing for each rooms, and guests expect individual temperature control. So with VRF, one room can be fully loaded, another room can be switched off, and another room can operate at partial load. The system automatically adjusts refrigerant flow, saving energy while maintaining comfort. This is something conventional DX systems struggle to efficiently manage. Next, let's look at mixed-use buildings. Mixed-use buildings combine offices, retail, residential or hotel spaces. Each of these spaces has different operating hours, different cooling profiles, and different comfort expectations. VRF system handles this complexity very well because of their zoning and control flexibility. However, there is an important point to remember. VRF is ideal for medium to large buildings, multiple zones, and variable loads. But VRF is not automatically the best solution for every large building. Once cooling load becomes very large or operation becomes 24/7 or fresh air and latent control dominate, we must start evaluating chill water system instead. So the key takeaway from this slide is simple. If your project needs flexibility, if your project needs zoning, and if your project needs energy efficiency at partial load, VRF is a very strong candidate. In the next slide, we will talk about what engineers must be careful about when designing VRF system, because VRF works beautifully only when it is designed correctly. Now, before we get too excited about VRF systems, there is something very important we need to understand. VRF is a powerful system, but only when it is designed properly. Many VRF failures are not equipment failures, they are design failures. Let's go through three most critical design considerations. First, refrigerant safety. VRF systems use large quantities of refrigerant. Unlike chill water systems, this refrigerant passes through occupied spaces. So as engineers, we must always ask, what happens if there is a refrigerant leak? Standards like ASHRAE 15 and ASHRAE 34 define maximum allowable refrigerant concentration and safety limits for occupied spaces. If we ignore this, indoor air quality is affected. Occupant safety is compromised and authorities may reject the design. This is why room volume calculations, leak detection, and ventilation strategies are not optional in VRF design. Second is piping limits. VRF systems have strict piping limitations. These includes maximum total piping length, maximum vertical height difference, and maximum distance between outdoor and indoor units. If these limits are exceeded, all return is affected, compressors work harder, and system reliability drops. This is why VRF cannot be routed randomly. Pipe routing must be planned early, coordinated with architecture and structure, verified against the manufacturer limitations. Ignoring piping limits is one of the most common VRF design mistakes. The third is control strategy. VRF system depends heavily on controls. Without a clear control strategy, indoor units fight it with each other. Energy efficiency drops and occupants complain. Controls must define how zones operate, how schedules are managed, and how part load operations is optimized. In hotels, offices, and mixed-use buildings, good controls are difference between success and failure. So, VRF is not a copy-paste system. It is a design system. When refrigerant safety is checked, piping limitations are respected, controls are clearly defined, VRF performs beautifully. So now let's move to a very important HVAC system, that is chill water system. This system works on a simple principle. Cooling is produced centrally and distributed locally. Instead of producing cooling inside each room, we generate chill water at a central chiller plant. This chilled water is then pumped through piping to different areas of the building, where it is used by FCUs, AHUs to cool the spaces. That is why we call it central cooling with distributed comfort. Now let's understand why engineers use chill water systems. Chill water systems are selected when building size becomes large, cooling load is high, operation is long or continuous, and reliability is critical. Unlike DX or VRF systems, we are not depending on many small compressors scattered around the building. We rely on a few robust chillers designed for heavy-duty operations and maintained in one central location. This makes systems stable and predictable. Next, we are going to understand the roles of FCUs and AHUs. So now let's understand the terminals. FCUs are typically used for rooms, offices, and individual spaces. AHUs are used for large areas, fresh air treatment, humidity control. This gives designers flexibility to control temperature, manage ventilation, and handle latent load effectively, something that becomes very important in hot and humid climates. Now let's also understand why chill water works well at a scale. As buildings grow larger, DX systems becomes inefficient, VRF system hits its piping limits and refrigeration limits. Chill water, on the other hand, chill water systems do not have these constraints. Water is safer than refrigerant, easy to distribute, and suitable for large vertical and horizontal distances. This is why chill water systems are widely used in hospitals, airports, large office buildings, data centers. Chill water systems are not chosen for convenience. They are chosen for reliability, scalability, and long-term performance. Yes, initial cost is higher, but over the life of the building, they often become most economical and stable solutions. Now let's move to a system that is very common in UAE and Middle East. That is district cooling. District cooling is fundamentally different from everything we have discussed so far. Here, the building does not produce its own cooling. Instead, cooling is generated by a central utility plant and supplied to multiple buildings through an underground chill water network. So from the building point of view, there are no chillers, no cooling towers, no large mechanical plants. The building simply receives chill water from the utility. Let's understand why district cooling exists. District cooling exists for one main reason, that is large scale. When developments become very large, high-rise towers, master planned communities, city districts, it becomes inefficient for every building to run its own cooling plant. A centralized utility can operate large, high-efficiency chillers, optimize energy use across many buildings, and manage peak demand better than individual systems. This is why district cooling is heavily promoted in dense urban developments. Now let's understand what this means for the building designer. From a designer's perspective, district cooling simplifies HVAC plant rooms, it reduces space requirements, and it removes major maintenance responsibility. However, there is an important shift. The building owner is now dependent on the utility and is subjected to cooling tariffs and is bound by the utility design requirements. So while plant complexity reduces, commercial and coordination complexity increases. Now let's understand the engineering reality of district cooling. District cooling is not optional in many projects. In many UAE zones, authority mandates district cooling and authority mandates chilled water connection as compulsory. As engineers, our role is not to debate the system but to design ETS rooms correctly, comply with utility standards, and ensure proper interface between building systems and utility supply. District cooling is a utility-driven system and ideal for very large project or developments, and is excellent when planned at master planning level, but is not selected based on preference or cost comparison alone. It is selected based on authority requirement, urban planning strategy, and long-term energy management goals. Now this slide is probably the most important slide in the entire session because this is where everything comes together. Let me say this very clearly. There is no HVAC system that is best everywhere. DX, VRF, chill water, district cooling, all of them are good systems, but each one is good only within its natural operating zone. Let's look at this from left to right. DX system sits on a small scale end. They are ideal when the building is small, when the loads are limited, operational hours are short, and simplicity and low cost matter. Trying to use DX for large building is like using a small car to pull a heavy truck. It will move, but it will suffer. Next comes VRF. VRF sits in the medium scale range. It is perfect when zoning is required, loads vary throughout the day, and partial load efficiency is important. VRF bridges the gap between DX and chill water. But once the building becomes very large or runs 24/7 or has heavy fresh air requirements, VRF starts reaching its limits. Now we move into large-scale buildings. Chill water systems are selected when reliability is critical, loads are high, operation is continuous, system life and stability matter. Hospitals, airports, data centers, these buildings cannot afford system instability. This is where chill water shines. Finally, we reach district cooling. This is not even a building level decision anymore. District cooling operates at a city scale. Here, cooling is provided by a utility. Buildings become consumers, not producers. Authority planning drives the decision. At this level, HVAC becomes part of the urban infrastructure, not just building design. So the real engineering skill is not knowing how to size the equipment or memorizing the catalog data. The real skill is knowing which system belongs where. Right system, right scale, right project. When we respect this logic, system lasts longer, energy use stays under control, clients are satisfied, and engineers will sleep peacefully. In the next slide, we'll talk about most common mistakes engineers make when this logic is ignored and how to avoid them completely. Now let's talk about something every engineer eventually learns, usually the hard way. Most HVAC problems on projects do not come from calculations. They come from wrong assumptions during system selections. Let's go through 3 most common mistakes. The first is copy-paste design. This is probably the most dangerous habit in our industry. A system that worked perfectly in one project will not automatically work in other project. Different buildings have different usage, different operating hours, different loads, and different client expectations. Copy-pasting HVAC designs without re-evaluating the project context leads to systems that are technically correct on paper but wrong in reality. Good engineering always starts fresh. Second is contractor preference. This one is very common. Sometimes a system is selected because the contractor is comfortable with it. Spare parts are easily available or the installation team prefers it. But comfort for the contractor is not the same as suitability for the project. System selection must be driven by building needs, operational requirements, and long-term performances, not by who installs it faster. And third is ignoring life cycle costs. Many projects focus on initial cost, but HVAC system operates for 15 or 20 years, sometimes even longer. If we ignore energy consumption, maintenance cost, reliability, and replacement cycles, we end up selecting the cheapest system, not the right system. And over time, the cheapest system often becomes the most expensive mistake. So good HVAC engineering is not about choosing the latest system or the cheapest system. It's about choosing the right system for the right project. When engineers avoid copy-paste thinking, stay independent of preferences, and consider full life cycle cost, projects perform better, clients are happier, and engineers earn long-term trust. Now let's pause for a moment and bring everything together. Across this entire session, we have discussed DX, VRF, chilled water, and district cooling. Different technologies, different scales, and different use cases. And that leads us to the first key takeaway. There is no universal best system. There is no HVAC system that works perfectly for every building. A system that performs beautifully in a villa may fail in a hospital. A system that works well in a hotel may struggle in a data center. Good engineering is not about choosing the popular system. It's about choosing the appropriate system. The second key takeaway is system selection defines performance. Comfort issues, energy consumptions, maintenance problems, and operational complaints are often decided before construction even starts. They are decided at the system selection stage. If we select the right system, design becomes easier, operation becomes smoother, and performance becomes predictable. And the third key takeaway is think life cycle, not just cost. Initial costs are visible, life cycle costs are hidden, but far more important. HVAC systems operate for decades. If we ignore energy consumption, maintenance effort, reliability, and system longevity, we may save money today, but we will pay for it in many times over tomorrow. Good HVAC engineering is not about shortcuts. It's about understanding the building, respecting the scale, and thinking long term. When we get system selection right, everything else falls into place. And with that, we come to the end of today's session. Thank you for taking the time to go through this discussion on how to select the right HVAC system for a project. If there is one thing I want you to carry forward from this video, it is this. Good HVAC engineering is not about copying system. It is about understanding buildings, usage, and long-term performance. When we select the right system for the right project, everything else becomes easier. Design, construction, operation, and maintenance. If this session added value to your engineering knowledge, please take a moment to like the video, share it with a fellow engineer or a colleague, and subscribe to Sustainability and Engineering. This channel is built to share practical engineering knowledge based on real projects, real challenges, and real experiences. Because in engineering, we just don't build systems. We build them right. We build them once. Thank you, and I'll see you in the next one.